Hello, and welcome to RF Capacitors in 5G. I'm your host, Jake Michaels. I am the Technical Product Manager for Ceramics. And today we're going to do a closer look at RF capacitors for 5G applications. All right, so the first thing we're going to do is what is RF? Well, RF stands for radio frequency. These are the electromagnetic waves that surround us every day. The absolute definition is the oscillation rate of an electromagnetic radio wave. Frequency, which is the speed of the oscillations, is defined by the speed of light divided by the wavelength. Now, the wavelength, if you look at the visual graph below, is defined by the two peak points of the electric field. Now, in an electromagnetic wave, there is an electric field and a magnetic field, and they are orthogonal, or at a 90-degree angle of one another, and they work in tandem. This slide shows the RF frequency spectrum and the various applications across the frequency band. The microwave band goes from 300 megahertz to 300 gigahertz, while the millimeter wave band is about 28 gigahertz to 300 gigahertz. On this slide, on the lower x-axis, we also show the wavelength and frequency. Wavelength, as we looked at on the last slide, refers to the physical distance between the two peaks of the AC wave, and it decreases as the frequency increases. Now, why are we looking at higher frequencies? Well, higher frequencies have both advantages and disadvantages. The advantages of moving to a higher frequency is a greater use of the frequency spectrum, right? So we've utilized all of these lower frequencies with all of these other technologies. So as we fill up and add more technologies, we need to utilize more of the band. So we're moving away from interfering with those other devices. Additionally, as we move to a higher frequency, we have a higher capacity or bandwidth to send more data in less time. So this is very important in smartphones and autonomous driving, that we can move data quicker in a given amount of time. When we think of 5G, the first thing that comes to mind is more data, and it's one of the reasons that we're operating in this higher frequency band. A disadvantage of using 5G or higher frequencies is it has a shorter range. Signals can be blocked by dense objects, and outside weather conditions can impact. This means that utilizing 5G technology requires more base stations. Because they don't travel as far, we need to place more stations along, and because they can be blocked by other objects and weather, we need to place more stations to overcome that fact. Now, most of us have heard of the rising 5G technology trends. The overall frequency range of 5G spans from less than 1 gigahertz all the way up to 40 gigahertz. 5G is actually separated in multiple frequency bands. You might have also heard it called the 5G millimeter wave. Some of the main applications for RF capacitors are RF power amplifiers, base stations such as 4G and 5G, key fobs, handheld radios, wireless LANs, wearable technology, and autonomous and connected vehicles. When you're looking at the actual circuitry in where these RF capacitors are used, they're used typically in DC blocking, matching, and of course bypass and filtering applications. Okay, so now let's start talking about RF capacitors. Specifically, what is the difference between a standard ceramic MLCC capacitor and an RF ceramic capacitor? Here we are showing some key characteristics for capacitors used in RF applications and what's important for design engineers. The first is the ESR at high frequencies. This is the resistance of the capacitor, which includes the resistance due to the dielectric as well as the electrodes. This is important because ESR is directly related to the power dissipation in the form of heat. High ESR can cause excessive heating in the capacitor, so we want that to be low. The second is Q, or quality factor at high frequencies, which represents the efficiency of the capacitor. Q is directly related to ESR in that lower ESR means higher Q because they are inversely proportional. RF capacitors have very high Q for two reasons: their low capacitance and their low ESR, so it's a two-factor reason why Q is a high value. ESR and Q, these top two, are by far the most important characteristics in RF capacitors. That's why they're often called high Q capacitors. Now, the third characteristic is the SRF, or series resonant frequency. This is the frequency in which the total impedance is no longer capacitive and begins an upward trend and becomes inductive. So the higher the SRF, the better the RF capacitor, since some applications require the designer to stay well below this SRF point. And lastly, TCC, or capacitance change with temperature. This determines how much the capacitor values shift at different temperatures. RF capacitors need to be very stable over a broad range of temperatures. So again, these four key characteristics in RF capacitors are very important for design engineers to consider. Now, after looking at those design characteristics, how do we optimize a ceramic capacitor to be favorable at high frequencies? Well, the first thing we must do is to choose the right dielectric for the capacitor. The design goal here is to choose a dielectric that provides very low loss and provides good capacitance stability over temperature and voltage. Typically, these are high Q class 1 dielectrics such as C0G or NP0. The next thing we do is choosing an electrode material that provides the lowest ESR and ESL over a broad frequency range. This means we stay away from ferrous materials such as nickel. To illustrate this, we have a plot measuring the resistance of a 1 millimeter copper wire compared to the wire made from nickel. At low frequencies, say below 1 megahertz, the resistances are pretty similar and the overall are very low. But as we move into the higher frequencies and we increase this frequency point into the RF range, we can see that the ESR of nickel starts to increase dramatically. This is due to the ferrous properties of nickel, and when designing RF capacitors, we stay away from it. So, no nickel. Since the majority of the resistive losses of an RF capacitor at high frequencies is due to the electrodes, the electrode material is critical. Now, the final thing is the physical geometry that plays an important role in the resistance and the inductance of the capacitor. Long and narrow capacitors will have higher ESR and ESL than short, wide capacitors. So, in some RF capacitor offerings, you will see a square case size such as a 0505 or an 1111. So now that we've covered the basics of RF and RF capacitor solutions, we're going to provide a couple YAGEO Group product solutions. So Chemet and YAGEO both offer RF capacitor solutions. The Chemet ones are called High Q CBR series, and the YAGEO ones are the CQ series. They both are high Q application frequency range capacitors, and they operate in this 5G microwave and millimeter wave band region. The Chemet launched the High-Q CBR series back in 2011 to aim at the RF power amplifiers, base station radios, and wearables. Since then, we've added some voltage and capacitance extensions, and we will begin end-of-lifing the 0505 case size, but they are optimal for high-frequency RF. The prefix starts with CBR, and case sizes are denoted by 2 digits. Everything else in the part number follows the same format as standard products. One exception with the CBR is the standard packaging is in a 7-inch reel with no C-spec required. Now, looking at the YAGEO high-frequency MLCCs, they have it broken into 2 different series, the CQ General Graded Series and the AQ Automotive Graded Series. They have case sizes from 01005 all the way up to 0805, and a cap range from 1 picofarad to 100 picofarad, with a voltage rating of 16 volts all the way up to 500 volts. It's a very similar internal structure. They have a copper electrode with a nickel outer layer and a tin outer shell. And then, of course, these apply to base stations, wireless phones, different wearables, and, of course, automotive driving. Looking at the HiQ MLCC roadmap, we look at the case size is actually denoting what application these are typically going to be used in. So for the 01005, which is extremely small, these are used in more smartphones, true wireless earbuds, PA modules. If we move up a size to the 0201s, we look at more mobile phones, Wi-Fi, and Bluetooth modules. When we move to the 0402s, we're also stepping up in voltage as we go along this. But at the 0402 level, we're looking at routers, micro base stations, and car T-boxes. And then above that, we're looking at base stations and car antennas. Looking at the ordering information, the series is denoted by the first 2 digits, either CQ or AQ. Next followed by the case size, tolerance, packaging, dielectric, voltage, termination, control code, and the capacitance value. So, the key takeaways from today. An RF capacitor is a capacitor whose characteristics are optimal at RF frequencies. So these applications include power amplifiers, base stations, 5Gs, wearables, autonomous vehicles, and connected devices. Both YAGEO and Chemet continue to expand the high-frequency series, looking at the 01005 case sizes and CBR automotive. And when looking to design with these, it's important to denote that you need a special set of E2DI tools that are provided as datasheet graphs, S parameters, advanced monolithic models, engineering kits, and long-tail stocking packages. With that, I'd like to thank you for your time today, and I hope you have a wonderful day.